All right, so this video is going to be on the limitations of electrophilic aromatic substitution, EAS, reactions, and synthesis of benzene derivatives. So we got a good amount to talk about. So we know that benzene with just bromine doesn't work, right? We know we need that Lewis acid in order for it to proceed with the halogenation. It's also not an addition, it's a substitution, right? That's just EAS in a nutshell. So let's say we have this toluene, right? We got bromine and our Lewis acid, and then we've got some options, right? So where does that bromine go? We know that the methyl group is an electron donating group, so it's an ortho-para director, right? So that means we're adding it to the ortho and the para position. Remember that ortho position, there's two of them, but they are equivalent. So if we're adding one bromine, we only need to draw one of those products. All right, so now let's say we've got this guy right here, a phenol, right? The OH group. That's got, and then we throw in the bromine and the Lewis acid as well. So OH is also an ortho-para director, right? And it is an electron donating group. But if you remember the chart given to you and in your book, the OH is at the top of that list on strong electron donating groups. And so it's kind of fancy in that it adds 3 bromines to the same benzene ring, all in one fell swoop. And so does the aniline, so the aminobenzene. And that's because, well, aniline, specifically, that NH2 group is at the top of the list, while OH is just below that. So they're both really strong electron donating groups. And so it's really hard to control this halogenation process. And so that's why this is considered a limitation, because you can't necessarily, under these conditions, you can't get just the addition of one bromine. You get what's called polyhalogenation, or many halogens added to it, right? So this will also occur with the OR groups as well as the NHR groups and then the NR groups. So the methoxy, for example, or ethoxy, the alkoxy groups, and then any amine that's got an alkyl group as well. All right, so something we can do to kind of overcome this limitation is, since they are such strong electron donating groups, what we can do is just ditch the Lewis acid and throw in, which is contradictory to that benzene by itself. But remember, we're comparing the phenol reactivity to the benzene, and benzene is just the baseline, while phenol is super reactive. And so what we can do is just throw bromine in, and we will get the monohalogenated benzene ring, okay? So, of course, we're still going to be at the ortho or the para position, okay? And this is, of course, going to be more selective and more controlled, right? So once you throw a bromine on there, you've in turn deactivated the ring a little bit, right? And so that's why we can't add more than one bromine under these conditions, and we only add one, which is great because now we have control. Okay, so all examples of polyhalogenation and halogenation without the Lewis acid will also apply to chlorination as well. So let me actually get rid of that Cl2. So it's just Cl, right? So we can add a Cl with just Cl2, or we can add many Cls with the Cl2 and the iron chloride. Okay, and of course, sorry, I forgot to put the limitations of halogenation are that was that specific section, because we will also have our limitations of Friedel-Crafts as well. So we have Friedel-Crafts acylation and we have Friedel-Crafts alkylation, right? They both have their limitations, of course. So we always got to talk about the exceptions to the rule, right? So let's talk about Friedel-Crafts alkylation, okay? So we have benzene, we have an alkyl halide, we have our Lewis acid, and essentially we already know we get our isopropyl benzene, right? So let's take a look at the mechanism real quick. Once that halogen attaches to the aluminum and makes that Lewis acid base adduct, we know for a secondary alkyl halide, it can just pop off to form that secondary carbocation, and it's stable enough to kind of float around, right? And benzene can then come along and attack that, forming your carbocation intermediate. But then after reestablishing aromaticity, we get to our final product, right? I'm not going to draw that out for you. You guys know how to do that. So that's what the two arrows mean. We got a couple steps, right? And we get to our product. Okay, so what's the limitation here, right? So let's look at the energy curve. If we have our, let me draw it out for you. This would be our carbocation intermediate. Remember, this is no longer aromatic, and so it's it's got a high energy intermediate right there. If we were going to add an electron withdrawing group to this, it would raise the energy of that carbocation intermediate, right? And so in turn, that raises the energy of the transition state as well as the activation energy. Okay, so let's say we had an electron withdrawing group on there with an alkyl halide and our Lewis acid. This will not proceed because the presence of that electron withdrawing group raises the energy of the intermediate to the point where we cannot overcome that activation energy, and it's just too unstable. And so we aren't able to do Friedel-Crafts alkylation when we have electron withdrawing groups, specifically meta-directors. So everything below the halogens, right? Your carbonyl groups to your nitro groups to your ammonium groups, like all of those bad boys. So that is an unfortunate limitation, but it makes for a good synthesis problem because now you got to be creative in making that, and you'll see that later. So let's take a look at aniline. It's a super strong Lewis base, and we have a Lewis acid present when we're trying to do Friedel-Crafts reactions in general, right? So what happens is we get a Lewis acid base adduct where the nitrogen attacks the aluminum, and this Lewis acid base adduct basically puts a positive charge on that nitrogen, right? It's no longer available to donate its lone pair to the ring. That's what was making this such a strong and activated benzene ring, was the presence of that NH2 group with a lone pair. So we took that away and we deactivated the benzene ring, and it's now just an ammonium group, which is an electron withdrawing group, right? And we just said we can't do Friedel-Crafts with electron withdrawing groups because it raises the energy of the transition state so much that we can't even climb that hill. It's the Himalayas. So reaction does not proceed. All right, so let's take a look at another thing. We got benzene, right? We've got our alkyl halide, right? Just the chloroethane with our aluminum chloride. Now, let's say we add our alkyl group, right? Let's just say we did it once. It makes it activated, right? Because what's a more activated benzene ring? One with an R group on it or one just benzene ring? Well, what happens is, since we just activated that benzene ring, oops, I forgot my extra carbon there. And that's still floating in solution. We have a more reactive substance than the benzene ring, and so what happens is you get polyalkylation. Okay. Now, this is simply just because the ethyl benzene is more reactive than the benzene, and so it's going to add an extra ethyl group to it at the ortho or the para position. Okay. Again, another limitation of the Friedel-Crafts alkylation. It's really hard to control. What you can do is actually just add an extreme excess of benzene. That way it's just statistically more likely to hit the benzene than it is the product, the ethyl benzene, as the reaction proceeds. Okay, so let's take a look-see at benzene and the Friedel-Crafts acylation. Okay, so we know the general process, the general mechanism. We form that acylium ion, gets attacked by the benzene, and reforms that, or reestablishes aromaticity. And this, of course, is a strong deactivator, right? So basically the reaction is going to stop, and we can't do Friedel-Crafts anymore, right? So we don't get polyacylation But then we also just have to keep in mind that we can't take this compound and do Friedel-Crafts alkylation either. So if we wanted a methyl group and an acyl group on there, we should probably consider doing it in the opposite order. All right, so that's pretty much it for the limitations on Friedel-Crafts. And so now what we want to do is talk about disubstituted benzenes. So like I mentioned before, when we added a bromine to that like phenol, we deactivated that ring a little bit, right? At least with respect to the phenol itself. So that's really the topic of discussion when we're talking about disubstituted benzenes and EAS reactions. Okay, so there's really three guidelines here. So when directing effects of the two groups reinforce one another, the new substituent is in the position directed by both of the groups. If the directing effects oppose one another, then the more powerful activator wins. But if it's if no substitution occurs between the meta substituent due to sterics. Okay, so I will go ahead and draw out some examples for you. Okay, that way you get what I'm saying. You're picking up what I'm throwing down. Okay, so when they reinforce one another, for example. So let's say we have this carbonyl group and a methoxy group, and we want to do a halogenation. Well, the methoxy wants to go ortho-para, and then the carbonyl wants to go meta, right? Well, the ortho position for the methoxy is the meta position for the carbonyl. So that's cool because it's the same spot, and therefore they are reinforcing one another, and we can go ahead and just add the bromine to that spot. No questions asked. Okay, so let's go ahead and take a look at when the two directing groups oppose one another. Okay, now this kind of works for two scenarios. Either they're both directing or like both donating, or one's electron withdrawing and one's donating. So in the case for both donating, we go with the stronger activator. So the phenol, the OH, is the stronger activator compared to the methyl group, and the positions that they want to put them at are different, right? So we're just gonna go with the stronger activator OH and put it at the ortho position with respect to the OH. Okay. Now, if it were an OH group and an electron withdrawing group of some sort, and they were wanting to go in a different spot, you always just go with the activator. The activator always wins, and because the deactivator doesn't really doesn't have a say in it because it's lame and it's destabilizing the intermediates, right? So no substitution occurs between two meta substituents due to sterics. So if we have like this methyl and the hydroxyl group or the OH, they both want to go ortho, which would be super cool. But there's too sterically hindered for that kind of reaction to occur, and so they are going to go to the ortho or the para position. And in this case, we have for the para to the OH is ortho to the methyl group, right? Perfect. And then ortho to the OH is para to the methyl group. So that's also perfect. And we would just end up at that position. Okay. Now, what we want to do now is basically synthesize some benzene derivatives. And this is more or less like a puzzle because, as I mentioned before, if you wanted to make a benzene ring with a methyl group on it as well as an acyl group, you have to be selective on the order, right? And so that's really what this portion is all about. If we want to add a methyl group and a nitro group, we also have to be careful on how we add that. For example, if we take a methyl group and we add the nitro group with sulfuric acid and nitric acid, that's a piece of cake, right? But remember, the nitro group is first of all, it's an electron withdrawing group, so we can't even do Friedel-Crafts alkylation. But let's say we could, it would be at the meta position, so that's not ortho to the substituents aren't ortho to one another like the desired product is. And so, whoa, simmer down. What we have to do is ditch that process. Again, we can't even do any like that if we wanted to, but on paper, right, we don't know that. That's a great quiz or exam question. But what we can do is the alkylation, and let's just say we got mono alkylation product, or we at least took that and then we nitrated it. So that, of course, is going to give us the nitro group at the ortho position. Now we would of course, get the byproducts, the para substituted nitro toluene, but we still get our desired product, and there's no way around getting that. So you can note, and you probably should note, that you would also get the para substituted product. So we've got this tri-substituted benzene. So this is a little bit more complicated, right? So what we want to do is, oh, you know what? We don't know how to make the OH yet, maybe. So we'll start with phenol instead of just benzene. We'll learn how to do that in the next video. But we can take phenol, and we know that it's a strong electron donating group. We also know that if we were to halogenate it, we would halogenate the crap out of it. And so we don't want to do it in the traditional sense. We could do the Friedel-Crafts alkylation, get that methyl group at the para position as well as the ortho position, but whatevs. And then we can brominate it. And once we brominate it, remember the OH is a stronger donating group than a stronger activator than the alkyl group, and so we get the bromine at the ortho position with respect to that OH. Okay, so that's going to take practice. I mean, I could do 8,000 of these, and you'll still probably need to just think about it on your own. So that's all the practice I'm going to give you, but let me know if you have any questions. Have fun.